Okay, let me begin by just reviewing some the computing of percentiles and quartiles. Percentiles and quartiles, these are points underneath the data at point. Then the center. To calculate the p times 100 percentile, p is a proportion. You multiply n plus 1 by p. That gives you the position. N is the number.
No. My easy has to come down. Yeah. Sure.
Now, if the position is an integer, then the percentile is the observations that is in the kth ordering of data. It's in the kth position. It's the kth observation that's going from smallest to largest. If the position is an integer plus a fraction, then it's between the mth observation, that's the integer just below k, to m plus 1, the next observation. It's a weighted average. The weight that's given it to it is the fractional part. So if the fractional part is greater than half, the percentile will be closer to the m plus first observation. If the fractional part is less than a half, it'll be closer to the mth observation. Another method. This is for computing quartiles, and this is the one I suggest you use because it's probably the easiest. Quite often they'll result in approximately the same value, both methods. Sometimes they'll be sometimes they'll be different. For large samples, the two methods will give you the same answer.
Wait. I'm about to have class you. So, stick it downstairs.
Professor Laverty, would you be able to mute the KO, please? His mic is kind of interrupting the lecture.
Okay. I've tried to mute everybody except myself. Okay. We also, as I pointed out before, we're having some construction done in our house. There might be some noise coming from that as well. That will be probably over in the next or the following lecture.
Hi, sorry, Professor. I got a quick question. What slide are we on? Are we on the third or the fourth lecture slides?
I'd have to check. We're on right now numerical measures of central location, and in that there will be measures of non-central location. So I think the first PowerPoint was the introduction. We've done that. The second one was techniques for describing data, histograms, stem and leaf diagrams. Then this one is the next one, measures of central location, measures of location.
Yeah, on the website, it's section 3 and the current slide. Well,
I'm towards the end of that.
Yeah.
That lecture.
It's
The current slide's 67.
Yeah,
wait. No, this slide right in here. Let me see. Let me see. Because it is. Guess it is 67. Huh. Okay.
okay.
And I will mute myself because
Okay,
I'm not an
so-
idiot.
Okay. So we're looking at a different method. This is for computing percentiles. This is not for computing other than the quartiles. The quartiles are the 25th, 50th, and 75th percentile. The first step is to order the numbers in increasing order. Then from that, you compute the median. The median will be the middle observation. If there's two middle observations, it'll be the average of the two middle observations. This is also called the hinge. So here are 5 numbers, 10, 15, 21, 7, and 13. Arrange them in increasing order. The middle, there's 5, there's a unique middle observation, that's 13. The lower mid-hinge, or the first quartile, is the median of the lower half. If the median was one of the observations, you drop it out. The lower mid-hinge is the median of the lower half. The upper mid-hinge, that's the third quartile, is the median of the upper half. So there's the 5 numbers. The median is the middle one, 13. It's one of the observations, so you drop it out to compute the other ones, 2 other quartiles. This just has 2 observations. The median is the average of those 2 of the lower half. So that's the first quartile. The median of the upper half is the average of the 2 largest observations. If you use the first method, you compute the position of the median. It's 0.5 times n plus 1, which is 3. It's the one that's in third position. Compute the position of the first quartile. That's 0.25 times n plus 1, 1.5. That'd be the average of the first and second observation. The position of the third quartile is 0.75 times 5 plus 1, 4.5. That's the average of the fourth and fifth observation. So you get exactly the same results. Both methods, this isn't going to always be true. For large sample sizes, it will be roughly true. Here's the computations done on verbal IQ. There's 23 observations. There they are arranged from smallest to largest. The one that's right in the middle, that'd be the 12th observation. There'd be 11 observations below it, 11 observations above. So the median is the middle observation, 96. The lower mid-hinge, the first quartile, is the median of the lower half. There's 11 observations there, so it'd be the one that's in the 6th position. The upper mid-hinge is the median of the upper half. If I was using the first method to compute median, 25th percentile, 75th percentile, I get exactly the same results. The position of the median is 12. The position of first quartile is 6. The position of the third quartile is 18. So many programs compute these. Excel computes percentiles, quartiles. Should point out that each program uses a different method. The methods differ, come up with different answers, but for large sample sizes, the different methods come up with roughly the same answer.
I have a dumb question here, but so if we have like even data sets, so the median would be like the average of like the two middlemost values, right?
Yeah, so you wouldn't include that in the lower half or the upper half, okay? So if you think of that observation, the average of the two middle observations, it's splitting the observations into two equal parts. There's a lower half and an upper half. When the median is an observation, when the number of observations is odd, the median will be one of those observations. Is it included with the lower half or the upper half? No, it's not included with either half. Now, what we're going to do is a graphical technique that's alternative to the histogram, to the stem and leaf diagram. The advantage of this technique is that it's very compact, and you can put on the same graph several data sets for comparison. It's called a box whisker plot. My daughter teaches math in London, England, and she mentions that actually the box whisker plot was developed by my mathematical grandfather. He was the supervisor of my supervisor. His name was John Tukey. To draw a box plot, you compute the hinge, the median, in the first two quartiles. Then you compute also the maximum and the minimum observation. So there's 5 numbers that basically summarize the data. The smallest is the min. Q1 is the point where 25% or below. Q2 is where 50% below. Q3, 75% below. And the max is 100% below. Then to draw, there's those 5 numbers for verbal IQ. The median is 96. Q1 is 89, median of the lower half. Q3 is 105, median of the upper half. The minimum is 80, the maximum is 190. Now to draw a box plot, a box whisker plot, you draw a box going from Q1 to Q3, and in the middle of that box, you'll draw a vertical line where Q2 is. And then you'll draw whiskers at the lower end of the box and the upper end of the box going down to the minimum and the maximum. So this is what it looks like. The ends of the box are Q1 and Q3, and then there's a line in the middle, Q2, and then the whiskers are going down to the lower half and the upper half. So in the lower whisker, there's 25%. In the lower part of the box, there's 25%. In the upper part of the box, there's 25% of the observations. And in the upper whisker, there's 25% of the observations. So there's the data for verbal IQ, the 3 quartiles, the minimum and the maximum. There's a box plot of verbal IQ. The minimum is the end of the lower whisker. The maximum is the end of the upper whisker. The box goes from Q1 up to Q3 and has a line at median. You could draw a histogram and it would be over top of this. You can also plot, have box with plots plotted vertically. You don't have to have them horizontal. There's box plots of verbal IQ and math IQ. They basically show how the data is distributed for those two variables. They're both about approximately the same. Two box plots are very similar. There's the box plot of initial reading achievement and final reading achievement. So you can see that final reading achievement is a little bit higher, and a little bit more variable, and it looks like it's positively skewed. You can see the shape of the histogram roughly from a box plot. If one of the whiskers is pulled out, that means it's probably positively skewed. So the information in the box, that's the middle 50% of the population. And then the minimum Q1, Q2, Q3, and the maximum, divide the population into 4 equal parts of 25%. Advanced box plots. These are going to try to show outliers. Outliers are extreme observations, wild observations. They could have occurred because an error was committed writing down their value, or they could be extreme cases in the population. If you have data on salary of a company, there's probably a lot of people who are making just a reasonable salary, and then a few who are making huge salaries. These are the outliers. We'll now consider drawing box plots where you identify the outliers. An outlier is a wild observation. To draw a box plot, you need the median and the two quartiles, Q1 and Q3. The difference between Q3 and Q1 is called the interquartile range. That's the length of the box in a box plot. To identify outliers, you compute fences. The fences are like fences around a prison. Two prison fences, two sets of fences. Everybody inside the fences are non-outliers. Somebody outside the inner fence, but not outside the outer fence, is a mild outlier. Someone outside the outer fences is an extreme outlier. The inner fences. The lower inner fence is Q1 minus 1.5 times the interquartile range. The interquartile range, the difference between Q3 and Q1. The upper inner fence is Q3 plus 1.5 times the interquartile range. The outer fences are computed in a similar manner, except we multiply the interquartile range by 3. The observations that are between the lower and upper inner fences are non-outliers. Observations that are outside the inner fence, but not outside the outer fences, are mild outliers. Observations that are outside the outer fences are extreme outliers. You plot the outliers with single with a single symbol. I'll plot them with a solid dot. So the mild outliers with a smaller dot, extreme outliers with a circle, and the non-outliers are going to be represented by a box whisker plot. Max is the largest observation within the fences. Minimum is the smallest observations within the fences. So this is what a box whisker plot looks like when you plot outliers. The fences, the inner fences are, you add to the upper quartile, the third quartile, and subtract from the first quartile, 1.5 times the length of the box, which is the interquartile. For outer fences, you'd go 3 times that. Observations in this range are mild outliers. Observations here are extreme outliers. Example. This was an example computed from data collected on 109 countries in 1995. One of the variables was population size. Of course, there would be a couple of outliers there. India and China, which had very large populations compared to the remaining countries. These are the variables that were measured. Population size, density of population density. I think Singapore was an outlier here. This one has a very high density. Percentage of population living in cities, religion, so on. Now, the variable we're going to look at is infant mortality variable. There's the data in an SPSS data file. I'll be telling you how to use SPS on Monday in the lab. There is a stem and leaf diagram of infant mortality. The stem is the first digit. The leaf is the first decimal digit. There's 109 observations there. The median is the middle observation. That turns out to be 27. This number here. Q1 and Q3, median of the lower half and the median of the upper half. Because the lower half has an even number of observations, it's going to be the average of two values. Q1 was 12, Q3 was 66.5. The interquartile range is the difference between Q1 and Q.
Is that supposed to be Q3 minus Q1?
Yeah, it's Q3 minus Q1 because Q3 is always larger. So I've got a typographical error there. The outer fences, the lower ones, you multiply the interquartile range by 3 for the outer fences, multiply it by 1.5 for the lower fences. So the lower one is minus 151.5, upper one 230. The inner fence is minus 69.5. Upper fence 148.25. Because this data is positively skewed, the lower fences are not that important. There's only one observation that's an outlier, that's 168. And it's a mild outlier. It's outside the inner fences, but not outside the outer fences. That's actually Afghanistan. That's the country that that data was collected from. So to plot that data with a box plot for infant mortality, looks something like this. The ends of the box are Q1 and Q2, Q1 and Q3. Q2 is the line. This is the minimum within the inner fences. This is the maximum within the inner fences. This is the one outlier. Another example. In this example, we're studying the effect of various diets, 6 diets, on weight gain. 3 of the diets were high protein diets. 3 of the diets were low protein diets. The three high proteins diets differed in their source of protein: beef, cereal, and pork. Similarly, the three low protein diets were different: beef, cereal, and pork. This is the data. There was 10 observations for each diet. So these are the three high protein diets differing in source of protein. These are the three low protein diets differing in source of protein as well. There's some summary statistics: the median, the mean, the interquartile range. I'll be talking about these later on. These are measures of variability, all four of those at the end. There's box plots plotted. The advantage of box plots is they're very compact and they're really useful for comparison. Here you'll see that the two high protein meat diets, weight gain was generally higher than all of the low protein diets. And if the source of protein for a high protein diet was cereal, weight gain wasn't shifted upwards as much. These look to be roughly, these four look to be roughly the same. These two look to be roughly the same. No outliers in this data. Conclusion: weight gain is higher for the high protein meat diets. Increasing the level of protein increases weight gain, but only if the source of protein is a meat source, beef or pork. The next topic is measures of variability. Variability measures how variable the data is, how spread out it is. There's several ways of measuring variability. Two of them are the ones that are usually used when the data is normally distributed: variance and standard deviation. The other ones are used when you can't assume that the data is normally distributed: range, interquartile range, pseudo-standard deviation. Pseudo-standard deviation and interquartile range are roughly the same thing, but it's been adjusted so that it's interquartile range adjusted so that it's of the same order of magnitude as standard deviation. The range. Range is, you find the smallest and the largest. The range is just the difference between those two. This statistic will be influenced by outliers, will be greatly affected by outliers. The interquartile range, you compute Q1 and QT, the first and third quartile. The interquartile range is just Q3 minus Q1. It's the length of the box in a box whisker plot. The range is the length of the whole diagram. The interquartile range contains the middle 50% of the population. It's the length of an interval that contains the middle 50%. In verbal IQ, the Q1 was 89, Q3 was 105, the minimum was 80, the maximum was 114. The range is 119 minus 80, 39. So that's length of an interval that contains all of the observation. The interquartile range, 105 minus 89, 16. That's the length of an interval that contains the middle 50% of the population. These are easy to compute. The range is slightly easier to compute than the interquartile range. The range is very sensitive to outliers, extreme observations. One observation that's extreme will increase the value of the range by a considerable amount. The next two measures are variance and standard deviation. These are equivalent statistics. One can be computed from the other. Variance will be just the square of standard deviation. Standard deviation will be the square root of variance. The sample variance. Recall that when we're commuting the mean, we add the numbers up and divide by n. The numbers, observations minus the mean, are called the deviations from it. Some of these will be positive. That'll be true if the observation is above X bar. Some of them will be negative. That'll be true if they're below X bar. In fact, if you add up the negatives and the positives, the sum of the DIs work out to be 0. So to get rid of the sign, we'll square the DIs and sum that. So this is these two sums written out in full. The sample variance is the sum of the DI squareds divided by n minus 1. Originally, they were divided by n, but mathematicians found the better divisor is n minus 1. This is denoted by s squared. It's the sample variance. Example, here are 5 numbers. The mean will add up the numbers, 66 divided by n. The mean is 13.2. There is, if I subtract 13.2 from each of these observations, there I get the deviations of the mean. If I square those values and add them up, I get 112.80. If I divide that by n minus 1, I get 28.2. That's the sample variance. If I take the square root of that, it's called the sample standard deviation, 5.31. The more spread out the observations are, the larger the term in the numerator under the square root symbol, the larger the value of s, the larger the value of s squared. Interpretations of s. For normal distribution, approximately 2/3 of the observation lie within 1 standard deviation of the mean. So if you go 1 standard deviation above, 1 standard deviation below, that range will contain about 2/3 of the observation. If you go 2 standard deviations above, 2 standard deviations below, that will contain 95% of the observation. Another interpretation, if you draw the bell-shaped curve, the standard deviation is the distance from the center of the bell-shaped curve to the inflection points. So about 2/3 of the observations will be in that range. About 95% if you go 2 standard deviations above and 2 standard deviations below. So example, suppose we've collected data on 1,500 males in the age range 60 to 65. We measured blood pressure and cholesterol. Mean blood pressure was 155. So that means that blood pressure measurements were all varying about 155. Mean cholesterol measurement was 230. So all of the measurements were varying about 230. The standard deviations tell you how spread out they were. Standard deviation for blood pressure was 12, for cholesterol 15. Suppose that the data is normally distributed. Then you can interpret those numbers. 2/3 of males aged 60 to 65 will be within one standard deviation of the mean 155. So that'd be 155 minus 12 to 155 plus 12, 143 to 167. For cholesterol, the mean was 230, standard deviation was 15, going one standard deviation below to one standard deviation above, you get a range that will contain 2/3 of the cholesterol measurements. If you go 2 standard deviations above, 2 standard deviations below, you get a range that will contain mostly all of the observations, 95% of the observations. So that's how you interpret standard deviation. To compute standard deviation, you have to compute this sum of squares. The difficulty with this formula is that when you subtract off x bar will likely have a lot of decimals. Xi minus x bar will have a lot of decimals. Xi minus x bar squared will have a lot of decimals. Here I'm giving a computing formula for the left-hand side. The computing formula squares the observations, sums the observations, sums that. You can, through example, through a bunch of xi values, show that both sides will compute the same. The advantage of this one, the right-hand side, is that the number of decimals in computations become less. So to use this identity, you compute the sum of the xi's, you compute sum of the xi's squared, square each xi, and then use those numbers to compute the left-hand side using the right-hand side formula. To get s squared, I divide by n minus 1. So this is the computing formula for s squared. There's the computing formula for s. Example, these are the 23 measurements on verbal IQ. The sum of the xi's is 2244. The sum of the xi squareds, so I'd have to square each xi and add that up. That's 221494. So the easiest way to compute the left-hand side is to use the computing formula on the right-hand side. 221494 minus 2244 squared divided by n, 2557.652. To get the variance, I divide by n minus 1. N is 23, n minus 1 is 22. To get the standard deviation, I take the square root of s squared, 10.782. Let me go back to a rough way of calculating this. This is very rough. It's the range divided by 4. 95% of the observations live between xi minus 2s and x bar plus 2s. So the maximum is probably going to be around x bar plus 2s. The minimum is going to be approximately x bar minus 2s. The range will be approximately x bar plus 2s minus x bar plus minus 2s, which is 4s. So if I divide the range both sides by 4. S is going to be approximately the range over 4. I would use this formula not to compute S, but to check your computations for S. Should be the same. So for example, for verbal IQ, the range was 39. 39 by 4 is 9.75. The exact value for S is 10.782, which is close to 9.75. The rough calculation is very useful for checking your calculation. The pseudo-standard. The pseudo-standard deviation is the interquartile range divided by 1.35. This 1.35 is related to the normal distribution. It makes the interquartile range approximately equal to the standard deviation when the data is normally distributed. So for the normal distribution, the pseudo-standard deviation and the standard deviation will be approximately the same. For long-tail distributions, S will be larger than the pseudo-standard deviation. For platycurtic distribution, these are ones with short tails, S will be smaller than the pseudo-standard deviation. Verbal IQ. Interquartile range is 16. Pseudo-standard deviation is 11.85. The standard deviation, which was calculated using a much more complicated, was 10.782. This is sort of in agreement with the pseudo-standard deviation. The next topic we'll do is maybe at this point I'll stop and I'll answer any questions. Again, the lab on Monday will show you how to use SPSS software. Everybody who has paid tuition will be able to access computer labs in the university. There's virtual computer labs which you can access from a remote computer. So I'll be showing you how to do that. So are there any questions?
So will you give will you give us links to like download like this SPSS software, whatever it's called?
Yeah, I'll tell you how to get that. There's a website on the university called VLab. That's allows you to go into labs, and there's a list of software that you can use on VLab. So I'll be showing you how to get onto that software.
Okay, thank you very much.
I got a question. So for the midterm on Monday, we have everything we need to know for it now, right?
Yes. And I'll be mailing it to you, all students, on Sunday morning. And the answers, you have to go on to like the Stats 245 webpage. Let me just stop sharing here. And share my screen. Okay, escape. Now, if I go into the home page I get my screen. Here's stats 245. This is the answer sheet for test one. To fill this out, you just click on this link and you would put in your first name, your last name, your NSID, your student number, and then for question one, you'd put in the correct choice, A, B, C, down to J, and do that for all of the questions. And then at the very end, there's a button that says submit. So you press that, and then it'll tell you your answers have been submitted. Now, if I go back to Microsoft Edge, I'll search the web for VLab.
Sorry,
This is
just a
this-
quick question about the SPSS software.
Yeah,
Does the university provide any way that we can download it onto our computer at home and not have to log into the VLab service?
I don't think so. Now, you used to be able to download a trial version, but that only lasted for a certain length of time, I think 30 days. You can still do that. And you used to be able to continue to use it after the trial version was over by setting the date back on your computer to an earlier date. I don't know if you can do that anymore. But to get VLab, okay, I click here. There it is there, the link to VLab. Now you have to put in your NSID and I think I have my password already there. Wanted me to put it in. So there is the VLab. If you look at all, common to U of S, here's the arts and science lab. There's other labs. These are the software that's all common to U of S. There's quite a few. These are geographical software. Mathematica is a mathematical software math lab. Going down to here, there's SPSS. You just click that and it'll open up SPSS.
I have a question.
Yes,
For the midterm on Monday, do we need to use this SPSS or that
No.
comes after this first
That-
midterm?
that comes after the first midterm. You don't need to use that. You won't be able, you don't need to use software on any of the midterms,
Oh, okay. Thank you so much.
but you will probably have to use your calculator to do some of the calculations.
Okay, perfect. Thank you.
Oh, I have a question about the midterm. Are you going to upload it soon, like on Monday? Do we have a due date for it? I'm not sure
Okay.
if you've already answered this question.
Yeah, the midterm is going to be sent to everybody by email on Sunday morning. And then the answers have to be submitted by 3:30 on Monday.
Okay, thank you.
So this is I'm now in SPSS. I'll be showing later how to use this. You have to have your data on VPN. So you have to connect to VPN. You connect there by putting in your password for your I don't know what. So now I'm connected to VPN, and so all of the data has to be in
Hi, sorry about the VLab. This might be a dumb question. Is the username and password our PODS ID username and
yeah.
same password?
The username is your INSID, the same as for PAWS, and the password is the same as for PAWS.
Thank you.
The only problem I've had is, for some reason, SPSS doesn't scroll when you're using VLab. So sometimes the buttons you have to press, you can't get at. There's tricks to do that, but anyway. For instance, here's open up a file. If I want to open up a file, okay, there I can find the file. Now this is not my documents on my computer, but it's my documents on my VPN point. Anyway. So I think I'll end the lecture at this point because I have another lecture in 5 minutes.
Sorry, Professor, real quick. Will you be recording the lab as well?
Yes, I will.
Okay, thank you.
Okay.
So one last question. What are the material on the first midterm on Monday? Is it like what number of
It'll be right up. It'll be right up to today. So it'll be sections 1, 2, and 3.
Thank you so much.
And it will be covered in the practice exercises for test 1. So I have to stop at this point, stop sharing, and we'll end